Hi everyone, good to see you on this beautiful Tu B'Shvat kind day. And today, I think it's appropriate for the time of the year, we'll be talking about food, we'll be talking about energy and how this all fits together for us, humanity. And before that, I'll just mention, we're getting near to the point where you need to think about interesting subjects for your final. In the exercise that you'll have this week, you'll also have more details of what is expected of you. You'll also see there's dates for each one of you already allocated to when are you supposed to present your final. If you want to change it because of any reason, try to see if you can find somebody in the day that you want to move to. You'll see the other people allocated to those dates. Try to see if you can maybe email them and find a way and you can switch among you and just let us know that you switched. And if you are not successful at that, write to us and we'll help you solve that. We also know that there are people that only recently joined because they were on reserve. So we'll be also opening up another extra date for finals that will be later, at the beginning of March or so. So we'll update you on that as well. And that will be available to you. Questions about that? Okay, I'll also say that in the spirit of the subject we'll have today, we actually have a standing invitation to write a paper on calculations by the numbers that relate to food and plants. And so we're going to submit a paper about it. We're working on all sorts of things. And if somebody would be doing a project on this that would be especially interesting, we'll invite them to come and join us on the paper. So if that gives you some motivation, you're welcome to try and think in that direction. And we'll be putting one or maybe more such examples, and you'll become authors or co-authors on this. Okay, good. So let's start with a concrete challenge for us. How high can you go with a snack bar? What do I mean? I mean, if I want to walk up, I don't know, up a mountain, how high can I go based on the energy that I have there? Question is clear? Any suggestions how to approach it? Okay, so one thing I want to know is like within an energy bar, how much calories do I have in it? And then what would you do next?
How much calorie do you need to go up distance?
And then how to translate between calories and energy into elevation. Okay, so let's try and do it together. So here's my snack bar. I'm wrapping it up. Unwrapping it, and then I'm trying to think how many calories do I have in a snack bar. Anybody knows anything about caloric content of food? What?
You can burn it.
You can burn it. Okay, so one way is to burn it. We won't do it right now.
Composition, sugars, proteins, fats.
Oh.
Like sugars would give you say 4 kilocalories. Fats would give you 9 or something like that.
Okay, so who heard this thing about this number of say 4 calories per gram for sugars? Anybody? Okay, so some of the people, maybe in associate.
7 for fats.
What?
7 calories for fats.
So I think 9 is often stated. And okay, so this is the sort of thing that you might know or not know. And as you remember in the spirit of the course, we want to know a few numbers that are actually useful in order to infer other things. And I think that's the kind of thing that's useful, is to know that like about 4 kilocalories per gram, that's for sugar. Oops. And 9 kilocalories per gram, that's for fat or lipids. And that's roughly what we're eating, right? What else are we eating?
Proteins.
Yeah, so proteins is also roughly the same number as here. Okay, so going back to our snack bar, what do we need to know next? Something about the weight of the snack bar. Anybody knows the weight?
30 grams.
10 to the power of 2.
Okay, so I think we could do, I think 30 grams is what I heard here. I think I'll buy that for my snack bar. We could also do it, like a lower estimate and the upper estimate, the geometric mean or something like that. But let's go with 30 grams. And I think it's mostly sugar, although there is some fat in it. So altogether, the energy content is roughly 30 grams times 4 kilocalories per gram. So that's about 100 kilocalories. So far, so good. Okay, still now, so we finished the first part. Now we need to go from this thing of kilocalories. By the way, this kilocalories, it might be a bit confusing because sometimes it's being talked as calories just, right? So there's this odd thing in nutrition that kilocalories is sometimes called big calories with a big C. And so what we're calling calories in nutrition is really kilocalories, which is thousands of calories. We'll see how that plugs into concrete calculation in a second. Okay, so we have that. And now how do we do the translation between eating this and climbing on a mountain? Any ideas? So you can do calories to ATP. Okay, so we can go that path.
You can take a classical mechanics approach, this work against gravity, and that will be energy, and then this is energy.
Okay, so there's like two suggestions here. One is through ATP, conversion to ATP, and how much ATP could help you. And that's a good one, although I would say a complicated one. Because we have to see what's the conversion to ATP and how do you change ATP in your muscles into elevation, and then there's like another extreme going back to our physics, mechanics background and talking about the fact that if you want to go some height, age, we know something about how much energy is associated with it. Anybody remember something? MGH, right. So the energy required is equal to M times G times H. If that doesn't ring a bell, I don't know. Okay, so now I want to connect, so I can try and connect between these two.
This will give like a maximum amount that you can.
Exactly.
It doesn't account efficiency.
Right. How high maximally? You are very right. And then we could also think about how can we make it more realistic. Probably we'll need to do, that's like the difference in a way between the second approach here and the first approach that talked about ATP and how that turns into something. So in general, I'm happy taking this path of if I don't know how to solve, the more realistic suggestion, I'm happy with solving a less realistic but, solvable. And then I could try and make all sorts of excuses or estimates, how much different it is. Okay, so in that spirit, I want to connect between this and that, but I have a bit of a problem. I know that the units that I'm getting here of energy, anybody remembers what are the units? Joules. Okay, great. So it gets in units of joules. So here is joules, and here is kilocalories. So I want to connect them somehow.
4.12
Okay, so 4.12 something something. Okay, let's forget about the point something. What is this for? It's exactly this thing that would translate us because you remember we're always allowed to multiply by 1. So what is the 1 that I want to multiply here? There's about 4 joules per 1 calorie. Okay, that's the relationship, and there's like this thing that a calorie is what would take to raise a temperature of 1 milliliter of water, 1 degree, around, 20 degrees, all sorts of stuff. Doesn't matter. In the end, it's 4 joules per calorie. Which means that I'm getting here about 4, so 400, but this is kilocalories, 4,000, so it's 1,000. Okay, so I have about 400,000 joules. Yeah.
And why is it 4 joule divided by 1 calorie? And not 1 calorie?
Okay, so this is, so the question is why 4 divided by 1, right? Okay, so I'm doing this trick which is actually surprisingly useful and not completely always intuitive, of like you multiply, I want to multiply by 1. What do I mean? I know that the conversion ratio is that every calorie is 4 joules. And then I'm doing this divided by this, and I'm also helping myself with the units, and then I know I'm right. Okay, so I have 400,000 joules, and that's supposed to be equal to my mgh. Okay, how much is m?
100.
Yeah, I like it. 100, so 10 to the 2 kilogram. How much is g?
10.
Okay, 10, and the units is acceleration, so it's meter squared second, if I'm not mistaken. Okay, so we can solve it, right? So age is equal to 4 times 10 to the 5 divided by 10 to the 3, which is 4 times 10 to the 2, or 400 meters. Okay, so next time you want to climb Mount Metzada, you could eat a snack bar, and if you do it 100% efficiently, you can reach the top.
No, but this is if you climb up, if you on a rope. Not
If you go
on a...
Yeah, so next time you climb with a rope up Mount Metzada, 100% efficiency, you'll get it that way. Okay, so let's analyze this second. So there is this thing about the efficiency, and this thing with the rope is like thinking about the fact we would just calculate just going up, and as pointed out here, you'll also be, you're taking some more elongated path. Good, so we should take that into account. If all go, what? So it might be that we'll be able to also say something about, how much is associated with that. I would only say, I'm not sure. Okay, we could try and see whether that's a significant addition or not. Okay, so don't take from this the message of my as a recommendation to what to pack next time you're going to Judea desert for a hike. It's more in order to give us this thing of how do we connect between this issue of like food, energy, and things we're interested in. Okay, that's the overall logic, and of course we did all sorts of simplifications here, and that's why it's just the maximal of going up a rope or whatever. Good. But you might ask me, so there's different things if we could unpack it, and that's what we'll try to do in the continuation of the lecture. For example, there is this thing. Right? I'm always curious about like the numbers that you need to know. Here I'm just talking about 2 numbers, this 4 and the 9. How does it come about? Yep. So I leave the climbing aside, and I want to ask you, why is it that sugar has 4 kilocalories and fat has 9 kilocalories? How come it's so much? Why is it so? Any suggestions?
The bonds.
What?
The bonds.
Bonds. Okay. What about bonds?
Fat molecules have higher energy bonds. They have either more of them or
carbohydrates have water in them, and it makes them less dense compared to fats, which are just saturated fatty acids.
Okay, so let's start with this first notion about, say, how energetic are the bonds, or how many bonds there are. Right? That's kind of like how I would, I think, also approach it. And then when you try to drill down into what it actually means, it's not very easy to get it, but actually there could be a simpler example, a simpler explanation that goes in line with the second point that's been talked here. So let's try to just very simply look at the composition of this versus that. Anybody remembers about, let's say, fat? You know, what is the chemical equation, repeating unit?
C10.
Yeah, so it's like C, H and H. And this repeats n times. So far, so good? Okay, so you don't need to know a lot of biochemistry for my course in food energetics. And similarly, if I want to do it for sugar, it's very similar. But instead of H, you have OH. You see, I'm so terrible at this. You agree with me on this? And this could be, I don't know, like a length of 10, this could be a length of 5 or 6, but for our purposes of back on the envelope analysis, that's enough. And now, what is going to happen? I'm going to do a reaction where I'm going to take this and add oxygen and get in the end, some CO2 and some H2O. And so there's some rearrangement that would happen here. But actually, if you look at the bonds, there's not so much difference in terms of like the bonds of the carbon here. They're going to turn into something there. So in terms of the energetics, it's not so immediately clear why this should be, this should be more energy than this. Not so clear in terms of either number of bonds or how energetic the bonds are, which was the first more intuitive concept. But then there's something else, and that is looking at the molecular weight of this versus the molecular weight of this. What is the molecular weight of this, of every repeating unit? It's smaller than this, right? So specifically, how much is this? So 12 plus 1 plus 1, this is 14 Dalton. Right, Dalton are these units of hybrid, proton plus something. And how much is it here? 12 plus 1 plus 1, 14. 12 plus 1, and then plus oxygen has how much?
16.
16. So how much is it together? 30 Dalton. So you see that in terms of the weight of every monomer or component, there's a ratio of about twofold. Which means that even if I don't need this explanation of, more energetic bonds or less energetic bonds. Maybe there are, I don't know, maybe something in this thing is more energetic than this or less energetic than this. But actually there's a much more, a simpler explanation. Just the fact that even if I'll do the same thing and get the same energy from rearrangement of the bonds, the fact that the unit here is twice as heavy as this, it means that for the same change, I would get twice as much energy here per unit mass, because it's per gram, than I would get here. So this thing about, if you eat lots of fat, you'll become fat versus sugar, it doesn't require like very complicated thing about, the quantum mechanics of the strength of bonds and how much energy there is. There's actually a pretty easy explanation just talking about, looking at the components and seeing how much they weigh. Which I thought is, when I saw this for the first time, I was like, wow, that's a really easy explanation with things that I knew from, way back that I never heard about that actually relates to life. Just a second, there was a comment there.
I just don't exactly understand if the sugar weighs more per unit. The sugar weighs more. How come it's the one with the lower energy.
Okay, great. So there's something not intuitive here. I love your questions. They really help me because they really show how, what do we need to learn in terms of between the intuitive sense of things and okay. So we see that sugar, which is this, weighs more than this, right? And then if it weighs more, it sounds like more of something. Okay. But when you think about energy content, it's actually the weight of things is divided by. Okay, right? It's energy per unit mass. So if you weigh more for the same energy that you're giving, so let's say exactly the same energy is released from oxidizing this versus oxidizing that, the energy density would be twofold in the other direction. Okay. By the way, it's a bit more complicated. If you do exactly the stoichiometry, it's actually not exactly the same number of electrons. So it's true, the point that was said before, that like there's a different number of bonds. That's also true, but it's to a lesser extent than the issue of the molecular weight. There was another question from the, yeah.
If you insert the proteins here, it would become more complicated than that, right?
Yeah. So as you saw, I elegantly erased the protein. Just because it's more complicated, it requires more, because there's the nitrogen and this and that. Actually, maybe it's a good exercise. I never tried it to see if you can derive it also.
Think about the same thing, and we have extra nitrogen and another extra carbon, and then that would make the molecular weight to be more than sugar, more than fats. But then we have the calorie density of proteins to be close to sugars, as we mentioned in the beginning.
Yes. So I think what happens there, but somebody will have to dig more deeply into it, is that there's also more bonds that are being rearranged in the oxidation process, and therefore you're also getting more energy. The elegant thing about this comparison is that there aren't many moving parts. Like everything goes into carbon dioxide. There, you have nitrogen, it goes into something else, depends exactly, urea, not urea, I don't know what happens there. So there's also, there's more details that you have to dig into. And this is life, right? So, I'm not saying I'm solving everything. I'm just giving you like a nice place where like looking at the numbers and you can make sense, you can rationalize them in a way that's much simpler than what you would have thought otherwise. There was another question or comment? Okay. So if anybody finds something interesting about the proteins, do let me know.
I was thinking that since in proteins we have essential amino acids, which is what are needed for maintenance of stuff in the body, probably they are used as it is, and they're not really a large component of them doesn't go in like giving you energy for the body, but just maintenance of your body.
Okay, so there's another point that's being raised here. Actually, some of the protein that we eat, instead, so first of all, you could break it down into the amino acids, but some of the amino acids, you're going to reuse them. And therefore, you might not be extracting all the energy that you can from them. So that's true, but I think when you're looking at those things, it's not like how much energy you'll be metabolizing, it's how much energy you could get if you were really oxidizing it. So if you were burning it, or whatever is the reaction. So if you're reusing it, actually you don't count that. So that's, Okay, good. I think we're done with that for now. So we talked about the finals, about the snack bar, and about the caloric density. And I want to turn into the subject of agriculture, which is very much related both to issues of sustainability, but also obviously food and energy. And I got to hear a statement that I'm very curious about, which was the following. In the next 40 years, we will need to produce more food than we did since the agricultural revolution. This is cumulatively, yes? Okay, so every time I hear statements, is the statement clear?
So for
Like they
next
say,
40
okay,
years-
humanity through agriculture in the next 40 years, 4 decades, will need to be producing more yield, more food than in all the history from since agriculture was invented. And every time I hear such statements, I'm really curious. Is it true? Very often, like people just, when there's a good statement and somebody, charismatic says it, you go with them and that's fine. I'm actually more in the opinion that, I'm enjoying, trying to see if it's a myth or it's really a fact. Usually it's a fact, but it's correct, but sometimes it's not. And the question is, how would I know? Yeah.
Does this refer to calories or mass?
Okay, so I don't know if they were actually thinking about calorie or mass. So the answer is I don't know. Does it matter?
Yes,
Why?
because
Okay, we could think about it, like whether it matters whether it's calories or mass. I would think that at least to the level of accuracy that I'm interested in, it doesn't matter so much. Because we're talking about the food to be produced versus the food that has been produced. So if the ratio of calories to weight did not change super significantly, like if we're growing kind of the same things or always then I don't think it would matter so much. But
in the next 40 years, probably something will change in how we produce food because it's not sustainable.
maybe, hopefully. Well, I think it should change. But let's go back to, let's just say, you choose calories, mass, whatever you want. The question is still, how do we do what's known as a sanity check? Okay, so I want to get your help in doing what is called a sanity check. Where we're trying to see if this makes sense or not. And sanity checks will take all sorts of, types and flavors. So every time it might be a bit different, or sometimes it's kind of the same. So let's try and do one of them. So how do we do that? Yeah.
First, find the time that it's these 40 years versus 20,000 years. And then find the amount of people from here to the next 40 years. So the cumulative or the total number of mouth fed, and then you can do per day or per year kind of thing. And then you can do the same thing for the last 20,000 years. And I think that's about it, right?
Okay, so let's try and do it together. Okay, so that's the spirit of what I think we should do. So let's start. What is easier to do? From now, next 40 years, or now, last between the agricultural revolution? What is easier for you?
I think
Okay, we go forward. Always look forward. Okay, so we have, so let's do it this way. So we have 4 times 10, 10 to the 2, 4 times 10 years. And then we need to multiply it by what?
8,
Number of people. 8 billion.
10 billion.
Okay, let's do 10 billion, because I don't know if it's going to stay 10 billion. So it's 10 to the 10 people. Okay, so we're getting about 4 times 10 to the 11 person year. Okay, I've introduced here these funny units, person year, which are actually pretty useful. It's I need to sustain this number, 410 to the 11, person across a year. Okay, and then I don't care so much whether it's many people for a few years or less people for many years. It's kind of it's a good unit to work with. Okay, person year. See you next time you use it. Remember, you learned it here. Okay, good. So this is the future. That was not so complicated. Okay, now let's talk about the past. Yeah.
Just one question regarding the future. We don't take into account the population growth.
Okay, so what about population growth? So I kind of like included it in the fact that I say, today we have 8 billion, I took 10 billion.
Okay.
So I think, it includes population growth. And in a way, you'll see like, assuming you don't think it will be 100 billion or that will go down to 1 billion, for doing a sanity check, everything goes in the range of like 8, 10, anything somewhere between there.
It might actually not be true though, right? Because this is an exponential growth, and in the case that it is, I have no idea, but I don't know how many people are expected for 2040. It might be another order of magnitude, and then we might be missing an order of magnitude here.
Okay.
I don't know. I'm just saying that. Might
Okay,
not take
Not in 40 years span though.
I don't know.
Okay, so it's very good that you raise this in the sense that, like as you say, like I don't know, like you say you don't know, but this is like the course where we learn how to know. Okay, so this thing also and it relates also, I think your point comes from this thing of like the statement of exponential growth, which is something that's being hammered into our mind. It's like exponential growth, who knows what's going to happen? Like it's, everything could happen. So I'm just suggesting, let's take it easy with exponential. It depends. On some things, exponential growth could do a huge thing. In some things, exponential growth, just like linear growth, because if you're looking close enough, there's not much of a difference. I think I've shown that, maybe at some point. But like if you look at a graph that looks like this, which is exponential, if you're only interested at some time interval like this, and you look inside, it's not very different, the exponential from a linear, if you just do like, you linearize it. Okay, so in that respect, this exponential versus linear, like this issue of exponential, we should see what is the domain over which we're looking. And specifically for the next 40 years, I think humanity is actually very close to being at a state where the population is stabilizing at about 10 billion. And I think that's the estimate for, at least until 2100, that like we're going to stay within this range, and then probably it will be going down. And I was actually expecting somebody to maybe mention that like there's a lot of talk now about humanity crashing in terms of population. So that also is not, you shouldn't take it, too seriously in the sense that like until 2100, we're still going to be somewhere between 8 and 10 or 8 and 11. What would happen after 2100? We have other things to worry before that, in the sense that there's so many things in the Earth system that are very, very troubling, climate change, tipping points, etc. So let's see how do we get there for now. Okay, back to us. So, okay, so we talked about change, and we talked about, growth. Another question about the past. So how do we do a quick sanity check on the past? So one way to approach it is to, you could take, a database, find somewhere a database, there's estimates for exactly what was the population of humanity with all sorts of different methods, and try to integrate it, right? That's what we need to do, to integrate the population, which is fine, but very often when you want to do such sanity checks, you don't have the time or to now sit and download data and integrate, etc. Although you can do that, but I'm looking for something which is quicker to do. And for that, I suggest to try and break the problem into not think about necessarily the exponential growth, but just think about, say, some periods of time. So, for example, any suggestion how to try and break that problem? Yep.
Maybe do bins of certain 1,000 years and say like the average in these bins was this and this and this, and then you make an average of that.
I like it. Okay, so if you had like, if this was the growth curve, you say let's take bins and do that. So how, when was the agricultural revolution?
10,000 years ago?
Yeah, so I think 8,000 years or something like that, something like 10,000 years. Okay, so I could break it into bins of like 2,000 years, 2,000 years, 2,000 years, 2,000 years. That's a suggestion?
More or less, yes.
Smaller?
I would
200,
go
200,
smaller-
200,
I would go
200, 200,
smaller
200.
as we get closer. Like I would do from 10,000 years ago to 5,000 years ago one bin, because things didn't really exponential. Things didn't really change there, and then maybe like do them shorter now.
Okay, so I like it. I think that's also how I would approach it. in the sense that like you don't want to have it's good to break it into bins because that's easy to calculate. And you don't want too many or too few, but you also don't want it to be the same bins because there's a lot that has been, very little that happened over 1,000 years, around the agricultural revolution, and a lot has been happening in the last 1,000 years. And therefore, the suggestion to do it in bins of different sizes. Okay, so for example, I could say, I'll take a bin between minus 10,000, it's like before present, BP, until minus 9,000. That would be one bin. And the next bin could be between minus 9,000 and, okay, I'll do it differently. It's a bit confusing this way. We could do last, let's say, 10 years. And then we could do 100 years before that. And then 1,000 years before that. And then the 10,000 years before that. You see what I mean? I'm breaking down into 4 bins. Last decade, the century before, the millennia before, all the rest, which is 10,000 years, 8,000 years, whatever. Good. Last 10 years, what was the size of the population of humanity? So 10 years times how much?
7
Yeah, so we're like at 8 billion. Or 7 billion maybe if we take the average of the last 10 years. How much is that? It's roughly 10 to the 11 person year. Okay? Plus 100 years. What was the population on average in the last 100 years? Yeah, so roughly, I know, like somewhere between 1 and 2 billion. Which gives me another 10 to the 11 person years. Plus, if I take the 1,000 years before that, so now we're going like around Middle Ages or Roman Empire or something like that. How big was humanity? Hard to say.
10 to the 8th.
So about 10 to the 8th, I would say. About 100 million. Probably less than a billion.
By induction.
But you're only talking about people used as agriculture, which wasn't like all Africa and all
Okay, so good point here. Like there's a fraction of humanity that was, like already enjoying the agricultural revolution. It's really agricultural, and there's some that are still hunter-gatherers or something like that. Okay, I think negligible. Okay, it's like this. It's a good point, like a good comment, conceptually. But in terms of the numbers, I would be surprised if, let's say, out of those 100 million people that we're talking about, maybe it's like 20 million, maybe it's 1 million. It's not the dominant thing. Okay, so you can see I arranged the numbers just so it would be nice and fun. So it's also in the same spirit. And then I could say the 10,000 years before that. Again, I don't know what was the size of humanity 10,000 years ago or 5,000 years ago. I would say it wouldn't be outrageous to say that it's about 10 million. Okay, it's like, I don't know exactly, but in terms of order of magnitude. So we're getting again about 10 to the 11.
It doesn't matter, actually, because if it's less than that, then it's not significant. So it won't
Yeah, although maybe then I don't have this at all. Okay, what do I want to say? You can see if I sum these 4 things, it comes nicely to this number, but don't take it too seriously. I'm just enjoying myself to show that like it comes to the same thing. You can see that it comes up to being roughly similar. Which means what about my sanity check?
Six.
That it passed the sanity check, okay? Okay, for once, nobody was trying to fool us. It is really a true example of the challenge that we're facing as humanity, about the fact that really in the next 4 decades we'll need to produce as much food as all of our history since the agricultural revolution. Okay, and you see, some of the numbers here are not completely accurate, but that's fine. It just says, it's not easy for me, or I can't debunk the statement. And this is what sanity checks are needed in order to do. And I think in the exercise you have examples of looking if you can do sanity checks on things, whether you can debunk them or not.
I just had a question about the question itself. So you asked that we will need to produce more food than we did since the agricultural revolution. And we have been very meat-heavy people for say, the last, until the last 1,000 years. So what's the definition of food here? Is it the food from the agriculture which came from the last 10,000 years?
Yeah, so there's a question whether, when we're talking about food, what is sort of like the food that we're consuming directly, or food that we're producing through agriculture and then feeding to livestock, and then we're eating the livestock, and then there's something happening along the way. I'll take that and let's deal with it soon when we're analyzing in the next step. But it's a valid question.
There's something about this sentence, this quote, that if you say 40 years, people think, wow, the next 40 years we're going to produce all this food. But if you're like in factor of 2, not in order of magnitude, in factor of 2, you are there like a mistake in here. So you're about like 100 years. It's like less. It makes this sentence like less, outrageous. You know what I mean? So this calculation is a bit like a factor of 2 years could change the whole thing.
In terms of our perception.
Yeah.
Okay, so there's a good point here that now connects between what we're used to, like as scientists, like something very objective and very numeric, data-driven, etc. And how do we perceive things? Okay, so for example, this could be done in easily three areas. One could be like in the next generation, we'll need to produce ta-ta-ta-ta. Or you could talk about 40 years, or you can say maybe it would have been 100 years. We did a factor of 2, which is not the big deal, and it would give us a completely different emotional sense about it. That's your point, right? So I think you're right. It's true, and it relates to the fact that, we're both scientific, and we're also, human. That we have feelings that relate and notions and what it means to us, etc. And you're right. I have nothing else to say. I would also say that, I think it's good to be aware of it, and also to be aware of it when you also, for example, like you're doing your scientific work, and now you need to report it in a paper. And actually sometimes a very subtle change in how you put the title of the paper, or how you write things in the abstract or in the paper, could make a big difference on how it's being perceived. And I think we should be aware of it. We could embrace it, we could decide not to embrace it, but it doesn't matter, it's going to happen. So we should be aware of it, and hopefully use it in order to tell your message and be clear in what you're doing, etc. But I agree with you, it would have made a difference here. Okay, in that spirit, let me just see how we're doing with time. Okay, so
Another thing. So what should I feel about this? Okay, so next 40 years I will need more food, but I can't do anything about it. Like people are going to grow, and it's not a bad thing to just need that much food. It's just a number.
Not
Should I
political
feel good
question.
about it? Bad about it?
okay, we need another, this is a different course.
Politics.
How, positive psychology and what should we feel about things, etc. And I also connect to that issue. For now, I would say this makes me be interested in the following question. I'm building some drama on what is the next question.
It's on the left-hand side.
How much land is needed to grow the food consumed by a person? Okay, we'll get to it in a second. Okay, the question is clear. So, like, motivated by this question, like, okay, should I be happy? Should I be not happy? At all, whatever. I'm saying maybe, but what you can is become curious about it. Given that we have this challenge, that maybe you're moved emotionally, maybe you weren't moved emotionally, but I think there's a statement here that makes you want to dig more deeply and understand more about what's happening here. And it leads me to the question of how much land do I need in order to feed myself? And I think soon we'll take a break and we'll let you, think about it and try to think if you can try and break down, if you can solve the problem, I'll be very impressed. It's also fine if you can't solve the problem, but just, do this divide and conquer of break it down into components. Say, if you give me this and you give me that, I will do this together with that, and then in the end I'll get an answer. That's also fine. But before we do that, there's a question here of I didn't mention a time period here, right? So what should be the right way to state it? What? Lifetime? Could be a lifetime.
How, the period of time takes to produce food?
Which is what?
A few months.
A few months. Okay. Okay, so how come? So did I forget it? So there was different suggestions here, right? To do it over a lifetime, to do it over a year, to do it over a few months. Yeah.
We can take the units from before, the people year thing.
Okay, there were units of people year from before that I could maybe take. So how come I didn't write it?
It doesn't matter because you can produce the food in more
Okay, so there's a claim here. Anybody could rephrase the claim?
It's not like you produce all the food and then you need to grow all of it again. It's always you plant new plants, and when some plants are in the middle of the growth, some are already ready to be harvested, and some are just.
So you're saying that in order to support what was said or against? I'm not sure I got it.
I think to support.
To support.
It's not like a clear time frame. Like here we harvest all the food in the world, and here we'll plant everything.
Okay, so there's a cute thing happening here that is not easy to. It's also not very intuitive, but that's why I'm spending a second about it. So in a way, you could say like a more intuitive way would have been, and I think that's what you were hinting at, the food consumed by a person in a year. Right? That would be the more intuitive thing. But then what we don't necessarily understand is like how much land it's like used for a year is needed to grow the food consumed by a person in a year. Okay, like every year, the land will be giving us me food, and the person will be eating food. So now actually the parcel of land, how much land I need, would be the same if I do it over a year or if I do it over 10 years. Okay? Now there's something that breaks here, because actually I want to say it's actually also true for a month. Okay, like whatever the land will give me in a month is what I eat in a month or in a day. But then you say, the land wouldn't give you every day the food. So that relates to the point that Yarden was saying. It's true that plants have this, their lifetime of doing things every few months. So you could do 1 cropping a year, 2 croppings a year, 3 croppings a year. So it's not like what you eat every day, but globally, different lands give you different things at different times. But on average, You can look at like what happens on average, and then the time units cancel out. And then it's like a land that continuously gives food and continuously you eat it. You can think about it that way. I think it's confusing enough that it's a good time for a break, and try to find, if you don't get it, try to find somebody who does. And think if you can try to do something to approach this problem, and we'll continue after the break. Okay, we have a big challenge in front of us. We need to feed all of humanity for the next 40 years, and we need to understand how much land it requires. And it's going to be a tough one, so bear with me. We'll need to think about it together. Okay, so this is the question. And now, any thoughts on the divide and conquer? So we'd like to break it down. It's difficult to come up directly with an answer. I want to start by breaking it down. So I'm starting from the end. In the end, I want to know land needed. Okay, so I think I can first break it down into two components, which is what? What?
Vegetarian versus.
Okay, so I would say that's advanced, the issue of what diet I would exactly be eating. It has an effect, but I think it's good to break it down into saying energy or mass or whatever you want per unit land and energy needed per person. Okay, if you haven't gone through that breakdown, divide and conquer, so that's like a first stage. Maybe there's a different way to do it, but that's a very basic stage to say, okay, how much land do I need? I want to know how much energy I need in total and how much energy I'm getting per unit of land. Okay, and again, instead of energy, you could do it per unit mass or something else that you like. Okay, we could talk about this in a minute. I think we'll be, Okay, how do we approach this? I can also, again, do a divide and conquer, which is how?
I thought about an average human.
Yeah. Okay, so I can convert that based on the caloric need. Okay, so this is going to be solved. Caloric need. This would be okay. Question is, how do we do this? How derive how much produce, energy, something else I'm getting from per unit land. So where does it all start?
I guess that if I didn't know the number, which I don't, I would go for various different foods, and I would try to first calculate how much calories do they supply, and then estimate how much land do each of them take, which is not that crazy different between different ones, right?
Okay, so you can try and do that. It's a question of how good our intuition is at doing that. I want to start from like the basic step, and the basic step is where does this energy come from? Yeah, so I'm interested in the sun energy per unit land and the conversion efficiency, solar to food.
But we don't really eat every part of the plant, right? We eat specific.
Okay, so we could try and plug that in as well.
I feel like that's way less intuitive, though. Like I have no idea how much sun energy per unit land whatsoever. I wouldn't even be able to.
Okay, so you know what? Let's not do it. No, I see your point. I agree. I'm taking like one path, and I agree that there might be a different path, and we could try it. There's like pros and cons for each.
I think we can take up at like wheat or rice because they are the most staple crops, and how much land is needed to grow like 1,000 kilos of wheat or rice, and then how much of wheat or rice is equal to say 2,000 calories a day because a person eats that much. So
Okay, so I have a rule. If like 2 people want that, we'll go that way. Okay, so let's say you want to do it. So how much can you grow? Like rice or whatever you wanted originally. How would you know how much you get per unit land?
Ask the farmer.
Ask the farmer. That's a good way. But the question is, whether were you carrying something in your head that could help us?
Yeah, I mean, I was gonna say, okay, let's go for tomatoes, for example. It's not staple. I think that's a really good way, but I have no idea how wheat or grains, like grains or rice. Grains and rice feels like the 70% water, which is really good. Kind of like most of our food is that, so go for that. But I would go for tomatoes, for example. I'd say, okay, you know.
Okay, let's take this concrete example. Let's say we did with tomatoes, okay? And let's say, we also found the farmer that would tell us how much growth of tomatoes they're getting per dunam or acre or hectare over a growing period. I would still have a problem with that because it's not easy to find exactly that, but let's say we're getting there. And I need to know how much is that tomato representative of the overall agriculture. That's a question. But then also there's the issue of the water content. Like how much calories am I going to get from that? And that could be confusing because like it could be 70% water, 90% water, 95% water, 99% water. And even though all those numbers like 90, 95, 99 sounds quite similar, we don't have a good intuition to this versus that. They give like a 10-fold difference into how much land do I need. I don't know if it's very clear. Between 90 and 99%, which doesn't sound like a big difference maybe, or like not an intuitive thing to know. Because you're interested like only in the dry weight, it's like between 1% and 10%. And I don't know if it's 1% or 10%. So I can easily get a 10-fold difference in my result.
But you do know how many calories are in a tomato.
You can try and do it that way. How many calories are in a tomato?
Like 50, 30, 50, like few tenths.
Okay, good. So you can do I think you can do it.
That's what I would do.
So I think that's a good one. You could try and approach it that way, assuming you know how much you get from the farmer and something about the caloric content of tomatoes and how much tomatoes is representative of other things.
Actually, yes.
Okay, we're on the same side. I think it's a nice way to approach it.
like if you look at the staple crops, most of them are dry, rice and wheat. And you don't have to worry about the water. And you eat most of what the rice or grain wheat is. And then I think that's a good approach in my opinion.
Okay, so that's a good approach, assuming now we need to know how much yield you're getting per, say, unit land per growing season or something like that.
Yeah.
Do you have it?
I can think, like say a hectare would give me say 1,000 kilos.
No.
I might be like not more than one order of magnitude away, but yeah.
Good. So I agree. We could approach it that way. It's in the same spirit, but just on a different thing that I think, let's say, is more representative, less of the problem with the water, but maybe you know tomatoes and you know better rice or something like that. Okay, good. So this is great, and you can try it out in full. Let me give you a few steps on trying to do it more from the, let's say, basic principles thing in a way, and like we could, it's also more complicated in a way. So there's advantages and disadvantages. Okay, let's start for a second about talking about this. How much energy is needed per person?
2,000 calories per day.
Okay, right. So we already have that value of, say, roughly 2,000 kilocalories per day. Okay, so we'll get back to it in a second. Let's talk about this thing of energy per unit land. And the first thing that we have is the solar energy per unit land. Okay, so how much energy is coming from the sun per unit of area?
What's the sun?
Ask the sun. Anybody's friends with the sun?
10 to the 26 watts joules per second.
That's overall reaching Earth.
Yeah, so you divide your area by the area of the
Okay, so if what's your name?
sun.
So if like Asaf, you remember something about the overall flux reaching the Earth from the sun, you can do a conversion from there. That's good. But let's say, yeah.
You know the wavelength, and you can just do by the wavelength of the sun. Then H bar.
Okay, you can start breaking it down like from photons and what exactly happens there. Let's say just let's try and use our way of estimate. Let's say I'm trying to think about how much energy when I'm sitting in the middle of the day and I have the sun impinging on me on a square meter, and I'm trying to think what is the equivalent of that with light bulbs. Okay. Okay, how do you know that? Yeah, but that's not exactly the spirit of what we're trying to do. It's true that like you can try and get it that way, but we're trying to see if we could estimate it somehow. Okay, but let's say if we already know that, how much, how many, we were just talking about in units of light bulbs. So how many light bulbs are in it, in 1,000 watts?
100? 10?
Yeah, so somewhere between 10 and 100 light bulbs per square meter. Which, if I was asking you before, I would expect you to say, somebody would say, it's at least 10, it's not more than 100 light bulbs per year, and then we could reach it, roughly that. Okay, so we have it. So the sun energy per unit length, it's also called as the solar constant. It's 1,000 watts per square meter. Okay, that's how much reaches from the sun, if it's above you. Okay, and now I want to connect between this and that. My problem is that it's not the same units. So what do we do? Yes, so we need to do some conversion of units. So let's try and do that. And I want to get from kilocalories per day, I want to get to watts. How do I go about and do that?
Turn it to joules, and then what is a joule per second, I think?
Okay, great. So let's try and do that together. And that's the spirit I'm trying to see. And I'm trying to do it in this way of like multiplying by. So I want to go from kilocalories to the other units of energy, which you mentioned, it's joules. Right? So I want to, in the end, I want to have I want to go to joules. And you remember we had 4 joules per 1 calorie. Right? So it means that for 1 kilocalories, I'll have 4 times 10 to the 3 joules. You okay with that? Okay, so we solve this. This would still not be watts, right? This would be, I'll get rid of this. I'll have joules per day. So what do I do from here onward? How do I get to watts? So I need to go to the seconds, right? Okay, so again, I'll have day here. And I want to have second here. Question is how many seconds? So it's 60 per minute times 60 for hour times 24. You see what I've done here? Okay, so how much is that? This times this, 3,600 times 24, 10 to the 5th.
But every square meter has like 10 hours of sun a day.
Oh, we'll get to it in a second. We're just playing with the units, then we'll talk about all the other aspects. Okay, so what do we have here all together? Just see that, maybe do it a bit more accurately. Yeah, I think that's something like 7 times 10 to the 4. Okay, would be okay. So I have 10 to the 5. This 2 times 4, let's call it 10. So I have 10 to the 3, 10 to the 4, 10 to the 7, divided by 10 to the 5. And what are the units? Kilocalories falls with the kilocalories. The day with the day. So I have joules per second, which is 100 watts, roughly. Okay, so each one of us, in terms of heat production, like in terms of food that we're eating at the rate of an energy content of about 100 watts in terms of power. it's actually a pretty useful thing. First of all, you could do some sanity check. Like if you think about like, okay, how much heat am I producing? So all of that food, you're doing some exercise, but most of it is going into heat. Just to see if it makes sense or not, you can think about, how many light bulbs are you the equivalent of in terms of how much heat you're producing. Things like that. Although it's not very easy to do because our area is larger than that of a light bulb or something like that. But actually, it's also like useful, for example, to think of how much air conditioning do you need in order to deal with the heat produced by people and things like that. And also, it's a nice, elegant number to know about yourself, that you're the equivalent of 100 watts in terms of power. So this is what comes out of 2,000 calories of food that we're eating per day. And now we also know that you have about 1,000 watts per square meter coming from the sun when it's just above you. What can you infer from that?
1 meter feeds you for 10 seconds.
Okay, so based on that, so you're saying 1 meter fits you for 10 seconds? Okay, that's interesting. That's kind of like different than what we said before, that we don't care about the time period.
10 people.
What?
10 people.
Yeah, so this could suggest that like 1 meter could feed 10 people continuously. If you were just eating the sun, literally, you were able to eat the energy from the sun. What?
The topic of efficiency.
Okay, so this was before we got into this issue. Okay, and things do become more complicated here. Let me touch on a few of those things. Okay, so first of all, this 1,000 watts per square meter, this is what arrives when the sun is just above you. But it's not always the case, right? So what do we have? What are the factors that would, like if I want to go from this was the maximal, the sun above you, what's like would be the average? What factors would come into play?
Between a factor of 2 and 4?
So what are different issues that would come that would lead to that?
Latitude.
What?
Time of the day, latitude.
Time of the day, latitude, albedo, seasons. Okay, so I have, for example, day and night would give me a factor of 2, right? And then there's the issue of like exactly whether the sun is above you or a different side. That relates to the period of the year and latitude and things like that. There's also cloud cover. Okay, if you do all of that, you come out that the average, instead of 1,000, is what's your intuition?
Between a factor of 2 and 4.
So a factor of 2 is too little because just the day and night gives me a factor of 2. Okay, so I have I have more factors that would have to come into play. So it comes out to about roughly 200 watts per square meter, so about a factor of 5. That's when taking into account all of that, like night versus day, clouds, time of year. Also the time of the day when the sun, with the angle, etc. So I have about 200 watts per square meter. This is what the plants could, work with, if you like. Okay, so now exactly. So now the issue is from this, what would be the conversion efficiency into foods? And for that, we could start breaking it down. I'm not sure I have time for that right now. And the result for me is actually pretty surprising. That, what would you think is the efficiency?
1%.
Okay, so I usually think about conversion efficiency. Let's say we're doing a conversion of we're burning coal or petroleum or natural gas in order to make our electricity in the power plant. The efficiency is on the order of 1/3. And that's true for many things that we do. Also in terms of things of our bodies, usually 1/3 is a good number for many such things. And then people were saying 1/10. But actually the person that said 1% is actually closest to the truth. It's somewhere between 0.5%. Something like 0.5%. So we could break down into why, and I'm actually, I worked about it, but it's just a bit complicated. There's many steps, because what needs to happen, just very roughly, you have the photons coming from the sun that give you 200 watts. About half of them are just not useful at all. Like you can't use them in photosynthesis. They're not enough in order to excite the electrons. Those that are good, that could excite the electrons, about half of their energy is wasted because there's like some equilibration with the electrons. They could only they're using some quanta out of it. So you're losing almost a factor of 2 again. So already a factor of 4. Okay, now you have this energy, and you need to use that in order to drive what's known as the carbon fixation process. So in order to do that, you're losing another factor of roughly 2. But then there's also an issue that sometimes you have too much light. It's very difficult for the plant to deal with the high light and the lower light. So they're also doing like photoinhibition. They're protecting themselves when there's too much light. So you're losing some factor as a result of that. And then from what you got from the carbon fixation, some of that energy you're respiring in order to, the plant also needs to respire at night. Other times there's like about a factor of 2 there. And then from what's left, part of it would be used for what is being eaten, for the grains. It's called the yield index, versus how much goes into other things that are not useful for us, that goes into the roots, goes into the trunk, and things like that. When you do all of those factors of 2 or whatever they are, you see that very quickly, just like 6 such factors of 2, and you're already at like about 1%. So altogether, it comes out to roughly 1 watts per square meter of agricultural food stored. And that's what we have to deal with. Like, we could try and improve those efficiencies in order to deal with this. I'm just saying it's not easy. Like, we've been trying to do this for like 8,000 years, and we got to about 0.5%. Yeah.
This last calculation about the efficiency is, it's not like big numbers, because you know this, because I assume that you know this from experimental data on all the different processes.
Yeah. Yeah. So you're right that like this overall thing is like what you will get exactly from the kind of spirit of the question that was suggested here, to look at tomatoes or look at rice, and you get that. And what I was giving you is a rationalization of how you can actually break down the different processes that happen that would give you this result. So you could look at from both angles. Okay. Taking all that into account, I know that I have much, much less. So now I can't feed 10 people with 1 square meter. Now what do I get? I actually need, as a result of this, 100 meters squared per person. Is that it?
That's assuming full efficiency of you eat everything that's produced by the plant.
Oh, okay, so let's say everything that was produced that is edible. But this is, you're right, this is not the case. There's also food waste. So we have to take that into account.
You will need to account for a diet, because people eat meat. This is if you only eat plants.
Right. So let's say these 2 things. One is the food food waste. The other is our dietary choices. That means that instead of eating that directly that way, it's actually worse. And it comes out as a result of those factors, mostly, and some others, that it's closer to 500 meters square per person. So what is this room? How much is this room? That's about, I don't know, let's say 10 meters by 20 meters. Okay, so we have 200 meters squared. So actually we need 2 such rooms in order to feed 1 person.
It's not accounting for water that this food needs to be...
Yeah, so now we're just talking about the land. There's also the issue of we could calculate how much water is needed and things like that. Each such thing, by the way, is a cool, direction for if you want to do a final project on this or that. you can try and estimate such things. So you can see there's like all sorts of places, and obviously this thing is the sort of thing that makes a huge difference in terms of our ability to feed ourselves. Let's try to verify for a second if that makes sense or not. If this is indeed the result, let's check it for all of humanity. How much land do we have? So, how much land do we need for humanity all in all? We need this times how many people?
8 to the 6, 8 to the 9.
So about 10 to the 10 people. So this is 5 times 10 to the 12 meters squared.
8 to the 9, 1 to the 10.
Make sense or not? I'm trying to do a sanity check on the result. What? So I could try and go from meter squared into kilometer squared, right? Which might be a bit more intuitive. How do I do that? I need to multiply. I want to get rid of the meters. I want to get kilometers squared instead of meters squared. Every 1 kilometer squared would be how many? 10 to the... So I have 10 to the 3 meters per kilometer, but it's squared, right? So it's 10 to the 3 times 10 to the 3, so I'll have 10 to the 6. So this gives me about 5 times 10 to the 6 kilometers squared. Just something strange. Yeah. No.
Do you have one extra?
Yeah. I need one extra something.
It's a folklore. You said 10 to the 10 persons. Is it not 10 to the 9?
Yeah, you're right.
No, it's the problem is with the 1 watt per meter
There's
squared.
8 billion people,
It's about
and you rounded it up to 10 billion. Now you're rounding it up to 100 billion. So it's 10 to the 9 persons.
No.
No? Any clear?
It's because the
No.
photosynthetic efficiency I think is about like 2-3-fold lower than what you use, and you like the harvest index is like a quarter, so there's 2 times 4 is a factor of 10.
Just 1 second.
Okay. Yes, sir.
I think actually, everything is okay. I was confused for a second. We came up with 5 million square kilometers. And I think the arable land, like how much is being used for growing crops in the world, is somewhere between around 10 to 15 million. So it didn't come out to be perfect, but it's within a factor of 2 or something like that, which is not unreasonable. Okay, I was blinking for a minute, but I think we're fine, and we could talk about the efficiency.
Well, I have a question just out of curiosity. Is the energy produced approximately the same as the energy that we would see? So if you're not talking about crowd, maybe about fish or product from sea.
Okay, so all of this is talking about food in agriculture on land. You could talk about what happens in the oceans. Overall, the fraction of our calories, but also protein, etc., that comes from the ocean is relatively small globally. There is some aquaculture of growing, so fish in the ocean, it's becoming a bigger issue, but it's still a tiny fraction. Overall, you could have, you're getting the same amount of solar energy, but doing the conversion, now we need to look at, see, what photosynthetic organisms there are there and what happens to them, etc. It's currently a very small effect on human nutrition overall. Now, whether it has potential for more, it could, but then there's other issues of nutrients and ecological impact and how do you, whether people want to eat it in the end, and all sorts of things like that. What comes out the efficiency? If somebody wants to do the efficiency of aquaculture, It's actually an interesting subject. But usually they don't go directly from sunlight. They actually hunt smaller fish, they grind them down, they put them there, and then the other fish eat them. So it's a different thing. So it's based on subsidies, either coming from this or they're taking things from agriculture that happens on land and feeding it there. Like all sorts of, so one could analyze what happens there. Okay, good. How are we doing with time? Not so great. Okay, but we did do both the human power, so you remember 100 watts, and we did do land for food in the sense that, let's say the key things to remember is that, even though you're getting the solar energy, solar constant of 100 watts per square meter, in terms of what you're getting in the end effectively for growing food, it's much, much less. Agriculture, unfortunately, is not that efficient, even though it's amazing. And you only have this, and as a result of that and how humanity uses this, we're actually needing almost all the land that we have available. And there was a question before that before the recess about our ability to actually have, the fact that we're cutting down forests, maybe we'll be able to supply more land, but that's actually, there's not that much more that's available to us, especially assuming that we don't want to cut all the Amazon forest, etc. It's kind of like the land area of China is about 10 million, yeah. But much of it, after you take off what's not available to grow agriculture, you're left with much less. Okay, good. As you can tell, there's a lot that we could dig more deeply into, but we won't have time for all of that. Let me just touch on one other, I think, nice example that relates to energy and us. And that is trying to look at the same kind of analysis, but trying to think about transportation. So, if I want to look, for example, at, I want to go some distance, and I can do it either with my car or with my bicycle. What would be more efficient in terms of the energy that I'm consuming, or let's say the greenhouse gas that I'm emitting? Okay. So we have this immediate tendency to think it's the bicycle, right? Cycling is better. But I just noticed that this issue of when you're cycling, you're also eating more food. And the production of food is not very efficient in terms of how much energy was needed and things like that. And so I'm interested to see overall, if I'm taking into account, let's say I'm looking at the greenhouse gas emissions, I'm not interested just in what I'm, also to look at what goes into the production of my food. That's my question now. Okay, so let's try and do it really quickly. So let's start with the car. How do I know how much greenhouse gas emissions do I have per distance that I'm taking? Anybody know something about your fuel efficiency? What?
Mileage.
Yeah, so how many kilometers are you doing per liter in your car? Yeah, so somewhere between, it used to be 10 would be a good number, but now with better efficiency cars, with hybrid cars, etc. So we're doing about, say, 20 kilometers per liter of fuel. Sounds reasonable?
You could keep with that.
Okay, so now I want to convert that into greenhouse gas emissions. So the question is, from every liter of fuel, how much CO2 am I producing? How much 1 liter of fuel turns into what? CO2. I don't know, where would it go otherwise? So yeah, so I'm combusting it. So if you think about it, so this question you can just do from stoichiometry. Because what is a fuel? Fuel is this, just carbon. And all this carbon goes into the CO2.
So it's like,
But you can also.
So just one second, stay with me. So it means that now I have the same number of carbons, but the weight of this also has the 16 and 16. The weight of this, the molecular weight, just like we did before, is 14 Dalton. This is just like we did lipids, right? You remember? And the molecular weight of this is 16 plus 16 is 32, plus 12, 44 Dalton. So I have a factor of about somewhere between 3 and 4. So this would give me about 4 kilograms, or because actually a liter of fuel is actually less than a kilogram, it's more like 3 kilograms, something like that. Okay, so it's nice to see you can derive it like without now knowing anything, except for maybe some chemistry. Good. So the rule of thumb of what I'm getting here, let's say, it's actually, I know in my Kia, I'm doing 25 kilometers per liter of fuel. So that means that my cost is about roughly 0.1 kilogram per kilometer CO2. So far, so good? Okay. Now I can try and do the same thing, or a similar thing. Now thinking about going with my bicycle. But I'm just not sure how much time we have for that. So let's say now I want to do it for the bicycle. How would we approach that? We need to again think about
how many calories we burn.
How many calories do I burn? How do I approach that? So just very roughly, I could say the following. Let's say for a second that I'm cycling for an hour. What distance would I cover?
10 kilometers.
More. No, 50.
I think 10 kilometers would be very, like it's almost what I would cover if I do very quick walking.
50.
So, okay, so, okay. We could think about it just like, we said here I was using somewhere between 20 and 30 kilometers per liter. I would say, if you're cycling, you're also doing roughly about 20 kilometers per hour. So it's really for the same 20 kilometers, you can do one of two things. Either you burn with your car like 1 liter of gasoline, or you cycle for an hour. So 20 kilometer cycling per hour. Another question is how many calories will you be spending?
That's a good estimate.
So how do I approach that? It's a tough one, right? Okay, so you remember, just to show you one way to approach it, I'm doing now a bit more quickly things. We said we're eating about 2,000 kilocalories per day, right? So that's about 100 kilocalories per hour, right? 24 hours a day. Okay, and now I could say, when I'm cycling, I'm roughly, let's say, doubling my energy intake. Somewhere around there when I'm not doing it's not the Tour de France of crazy cycling. It's about doubling. We could dispute that, but we could discuss that's like an order of magnitude, like another 100 kilocalories extra. So in order to achieve that, I need about 100 kilocalories per hour.
Didn't we say 200 if it's your doubling?
Yeah, so I'm saying whatever I have as my as my maintenance, or whatever I'm investing anyway, that's not as a result of me cycling. That's just for me being alive. This is the extra thing that I did for the cycling. Is another this 100 kilocalories. Okay, I'm saying that I'm starting to run out of time. We could. Let's see how to approach it in the. Whether we could do a quick. Okay. We could, for example, say 100 kilocalories. How much is that in terms of weight? Like when I'm doing the comparison to the fuel is mainly lipids. It has about 10 kilocalories per gram, right? That's what we did before, 9. Okay, let's make it 10. It means that in order to get this 100 kilocalories, I only need about 10 grams equivalent of lipids. So it's 100-fold more efficient, just like as a rule of thumb here. Okay? So we could do the conversion, but what you'll get is that the cycling, in terms of the energy needed, is say about 100 times more efficient. And then the next factor that you have to say, okay, in order to create my food, did I need to invest some greenhouse gas emissions? And today, the efficiency of agriculture, or the subsidies in order to do agriculture in terms of fossil fuels, is roughly a ratio of 10 to 1. Meaning for every calorie that we're eating, there's another 10 calories that came in order to run agriculture. Anybody knows for what? What are the main things for which you need to have greenhouse gas emissions in order to create our food? What?
Transportation of the food.
There's the transportation of the food. Actually, a pretty small effect.
The cows.
Fertilizers is a big effect.
Storage.
There's storage. Let's write it for a second. It's fun. So what do we have? We had transportation. We had storage. We had packaging that is being said.
Watering.
Deforestation.
Okay, just before that we had fertilizer. Okay, so we also have things like tractors, and all sorts of things that do the work in the field. I think I'm missing one other thing. So we have this investment, the fertilizer investment.
Water source.
Okay, there's some extra thing. I'm blinking for a second.
Somebody said that then deforestation.
There's the effect of deforestation. That's also true. Okay, all of those things together, I'm not getting into the factors of how much each one contributes at every given time. There's also the fact that, a lot is coming from the fact that we're eating, our diet is also composed of livestock. And those livestock, they're not very efficient, but also there's methane emissions and other emissions as a result of livestock that are potent greenhouse gas emissions. Altogether, you're getting about a factor of 10, that for every calorie that we're eating, somewhere in the agricultural systems, 10 calories of fossil fuels had to be burned. Which means that even if I include the issue of that inefficiency, instead of being 100 times more efficient with the bicycle, I'm 10 times more efficient with the bicycle than driving my car. And that's roughly what I wanted to tell you about it. Okay? In a funny way, it's not also unlike, so for the same 10 kilometers, I have a choice between emitting 4 kilograms of carbon dioxide in the usual way by a car versus 1/10 of that if I cycling and I take into account all the emissions that result from the extra food that I'll be burning. By the way, it's not unlike the ratio between the weight of the car and the weight of the person with the bicycle, which I think is pretty nice. Okay, so we'll end with that for today. I hope you got at least something out of all those aspects of our food, energy, etc. Eat the right things over lunch, and we'll meet next week. This would be the last lecture, and after that, we're starting with the final project. We'll have a week afterwards for you to take it easy of recess before that. Good.